I'm gonna open these and let me close this. So basically, we're going to take this example and we're actually going to code it. So basically, I have this. Let me do these side by side. So basically, I have this set up here. Basically, we have a main method, and then we have a isDistinct method that's going to check if all values in an array are distinct. So there's basically no duplicates. And then, so the first thing we'll do is we're going to copy the spec blindly. So let's see what happens if we copy it blindly. So basically that's saying for all I is from 0 to length of s minus 1, so you can just think of that as a loop. So we're going to do for int I equals 0, I is less than nums dot length, then I plus plus. And then basically another thing I should point out is in this MIS notation, this means that it goes I goes from 0 to s minus 1 inclusive. So it's saying that I is going to start from 0 and it's going to go up till s minus 1 rather than less than s minus 1, which is typically the notation in programming. So you wouldn't do like minus 1 here because the notation in the MIS is saying it's going to go up till s minus 1. So you would do less than, just as you normally would, less than nums dot length. And then we're going to have a nested for loop. So we're going to have j equals I plus 1. And the reason it's I plus 1 is so that I and j are never equal, basically. And then we have j is less than also nums dot length and j plus plus. And then basically if nums at I equal nums at j, we're going to return false. That's because we know that we found two elements that are equal, so they can't be this array can't be distinct. So we're just going to return false there. Otherwise, we can return true if we never find two elements that are equal. So if we go ahead and run that, so if we do Java C, true, that it is distinct. So we're printing out this list, whether or not it's distinct. But if I add a duplicate number, let's say 1, so it occurs twice, so we should see false now. Let me clear. Yeah, so we see it's not distinct. So this is fine. You know, we follow the spec, it works. But can anybody like think of any downsides to this? You know, what's potentially wrong with this? Or what things should we what should we sort of consider when just following the spec? Well, it won't be out of bounds because we have the nums.length is less than like j is less than nums.length and so on. So we don't have to worry about that. But think more in terms of, I guess, sort of the, yeah, so someone mentioned efficiency. So if you were to actually analyze the efficiency of this, this would run in, I think you guys have seen the big O notation, but if not, it's very intuitive. Basically, you want to state the complexity, which means basically how long does this program take to run? And that's going to be proportional to n squared. The reason for that is, let's say you have n elements. So you're going to do this outer loop, and then you're going to do a nested loop that goes through every element inside. So basically, you're going to do n elements and then n elements inside of that and so on. So basically, the way you state this is it's O of n squared. So you might see this in your algorithms course, but that's the sort of the time complexity of this. And then you also have memory usage. Anybody have an idea what the memory usage is? What's our sort of our memory cost, or is there any additional memory cost? That's time complexity is O of n squared. What about sort of the memory usage? Yeah, it's constant, which we usually write as O of 1, just because it's like a constant, it's fixed. The reason for that is, you know, if you look at the function, we don't make any additional arrays or anything like that. We just iterate over what we already have, the nums array. But you know, now you can ask the question of whether or not is this a good solution or not. You know, n squared is pretty bad if you think about it. Like this is an innocent example. You have it's like 6 elements. Let's say you had like 1 million elements, right? Is that a good idea to use this? That's going to run in 1 million squared amount of time. Is that a good idea? Probably not, right? So that should get the point across that following the MIS blindly is not always the best idea, because again, you might have performance issues, memory issues. So what we're going to do is go ahead and implement a slightly better version. And this is sort of outside the scope of this tutorial, but just to get the point across that you have, you can have different implementations and they don't always map exactly to the MIS. So we can use a slightly different example using a map. So I'll show you guys how this works. Basically, the idea is that, I think this is how you instantiate. Maybe there's a better way, but you guys should get the idea. Basically, what we're going to do is we're going to maintain a map, and then we're going to look at all the elements we've already seen. And then if we see an element twice, that means the array can't be distinct. So the reason this would be better is we would only do one iteration, and you'll see why in a second. So basically, we'll do for int I equals 0, I is less than nums.length, I plus plus, and then basically we're going to do we're going to basically put each element into our map. We're going to do map.put, and then we're going to use, for the key of the map, we're going to use the actual number because we don't want that one to exist twice. The value doesn't really matter. You can put 1, you can put I or whatever. I'm just going to put 1. Now we put it, but we also want to check if it already exists. So we would have to do map.contains key, and then we can do nums at I. So if the map already contains nums at I, we know that we've seen this element twice, so we return false. Otherwise, we put it in the map. So I'll go over this in a second. And just to clean this up, we can say, let's see, we can say int key is nums at I, just so we're not accessing that index twice. To clean that up, we have key. Okay. Yeah, you can use a hash set. I just want to get the point across quickly. Basically, we have a key, and then basically if we see it twice, so you can imagine you iterate through this list, 1, 2, and so on, and each time this condition is false because none of those numbers are already in the map. So 1 isn't there, 2 isn't there. So each time you're just putting it in the map. But what happens when you get to this last element is this condition ends up being true because you already have a 1, which was the first element, in the map. So you know that you found a duplicate. So that you can return false right away. And then if you never basically return false, you can just return true. So the code itself isn't that important, but the point I'm trying to get across is this specific implementation has much better performance. So this runs in, the time complexity of this is O of n, because notice we're doing a single for loop. But does anybody know what the memory usage of this is? Memory usage. Yeah, so can you explain why it's O of n? Just so it's clear for everybody. Yeah, so if you notice, we're making a map, and what we're doing is we're going into the map, and then we're putting each element. Now, sort of in the best case example, you could have like 1, 1, and in that case, you go through this, you find the number 1 twice, and your map only contains 2 elements, so it's almost like constant memory usage. But if in the worst case, if the duplicate element was all the way at the end, you would end up putting every single element basically from this list into your map. So your map would end up being basically the same size as your input array. So it's basically proportional in the worst case to your input array, which is also n. So basically we have time complexity is linear, memory usage is also linear. And let me rename these. These are distinct 1 and 2. So basically the point I'm trying to make now is, we followed the spec directly and we ended up with this pretty bad performing code, but we did something slightly more clever and we ended up with much better performance, which is proportional to n rather than n squared. But notice we made this little trade-off here. So now we have more memory usage, whereas before we had a constant amount of memory usage. So in reality, there's no right or wrong answer. And it really comes down to your sort of requirements and what you value more in your particular problem. Basically what happens is, maybe let's say you're designing like a web page, let's say on like Facebook or something, and you want to load all the friends of a user, right? And then maybe you want to compute a particular, you want to compute some data about the friends, maybe aggregate all their names into one list with their profile pictures or something. And maybe the approach to do that can be done in n squared. Now you might say, I don't really care about how fast the page loads and how fast that list of friends appears. All I care about is that I don't want any excessive memory usage and I don't want the browser to use up too much memory on the user's computer. So you would probably go with this solution in that case. Maybe, maybe not, but it's possible that you would pick this solution because you're saying I don't want any excessive memory usage and I don't really care if the page loads slowly, so I'm okay with having a bad performing solution. But let's say your requirements were slightly different. You're saying that I want to be able to load my page as quickly as possible, and it's okay. I'm okay with sacrificing a little bit of memory. It's okay if the browser takes up excessive memory on the user's computer. Then you might go with this option because it performs much better, and you're saying that you're okay with sacrificing memory. So it really comes down to trade-offs and the particular requirements, for your problem. And this is exactly the type of thing that you would see in like coding interviews. So the reason I brought this up is because it's very relevant. This is a question on LeetCode as well. So LeetCode is like this website that has a number of different coding problems that you'll often see in real interviews. And this is, a relatively straightforward problem, but it really gets the point across is that you can have different solutions, and then, some of them perform better, some of them have different memory usage. So you need to sort of understand the trade-offs that you're making. So you can imagine if you're in an interview, you might get a question, and then maybe you start with something like this, and then maybe your interviewer will ask you to refine it to something that performs better, but then now you have to discuss the trade-offs. And then again, there's no right or wrong answer because, as I mentioned, it comes down to what your particular requirements are and what your, what your needs are. So again, if you don't care about memory usage, you can go with this. If you do, maybe this is a better option, right? And so you have to make sort of these compromises. This is the sort of thing you would see in coding interviews. And again, this isn't isolated to just small coding problems. Like I gave that example of like a web page, right? So these are like design decisions that you have to make at basically all levels of the software development process. So hopefully that should be clear. And again, that should have gotten the point across that you can't always just follow the spec blindly. And we discussed why, and there can be different solutions and you have trade-offs between them. So that's all for the lesson. If you have questions, I'm going to stick around till 4:30.